we're going to study what's called simple harmonic motion. So if you take a mass on a spring like this and let it go up and down and up and down, this is a classic example of something in harmonic motion. Harmonic motion, and this would be an example, in fact, of something in simple harmonic motion. I'll explain how you qualify for simple harmonic motion status in a moment, okay? But it's harmonic in the sense that it's periodic or just keeps oscillating back and forth. Now, we are going to look at the classic mass attached to a spring. We're going to leave it horizontal for a second and derive the equations for this. I want you to notice a connection between a harmonic oscillator and something moving in a circle, because they are connected. We'll get to that in just a little bit. For starters, let's look at mass on a spring and how this qualifies for simple harmonic motion status. So here's the mass M, attached to this spring with a spring constant K. And this point right here is equilibrium. If I take this and I displace it either to the right or to the left from equilibrium, then when I pull this thing to the right, so if I displace it to the right, the spring is going to pull back on it towards the left. If I compress it to the left, the spring is going to push it towards the right. The spring is always pushing or pulling in the opposite direction that the mass is displaced. So the force of the spring, which is what we call a restoring force, restoring force. So that's S for spring. Sometimes you might use an R for restoring. But the restoring force of the spring is opposite the change in position of the displacement of the mass. This is Hooke's law. Remember Hooke's law? We did a lab on that at one point. So F equals negative kx. The negative sign is important. In order to put this into harmonic motion, the force is always opposite the direction it's displaced. Again, if I pull this to the right, the spring, so it's moved to the right, the spring pulls to the left. Negative sign. K again is the spring constant. So if I let this thing go back and forth, let it go, it's going to oscillate back and forth, always trying to regain its equilibrium position but passing through it. If we assume this is frictionless, this would go on forever as it goes back and forth. If there is friction, then it would decrease its amplitude over time. We call that dampened, D-A-M-P, damp. We dampen the oscillations until it eventually stops. So Hooke's law is kind of the governing law for all of this. Now you know that that's true, and also for something that's horizontal with the absence of friction, you know that F equals ma. And so by putting those equal to each other, you can calculate the acceleration of a mass on the spring. All right? Newton says force equals mass times acceleration. Again, this is in a frictionless environment. And then the restoring force is negative kx. If you solve for acceleration, the acceleration is negative k over m times x. You want to remember that for a mass on the spring. So next question, you ask yourself this. Where do you maximize the acceleration? Acceleration is maximized at the maximum position from equilibrium. Acceleration is 0 at equilibrium. All right, at equilibrium, x is equal to 0. Again, what is equilibrium? If I just let go of the spring, don't push it or pull it, the mass, I mean, it's just going to stay right there. I give it a shove either right and left, and it's going to displace from equilibrium. Where do you have 0 equilibrium? Zero acceleration at 0 position at equilibrium. You can maximize your acceleration. It's going to be at maximum amplitude. As this thing goes back and forth, that's how you'll maximize your acceleration at maximum amplitude. Okay, amplitude being the maximum displacement. So whatever, as this thing oscillates back and forth, say I pull it over here to this point right there, some amplitude which we use an uppercase A, let it go, then it's going to accelerate, it's going to have its maximum acceleration. Notice its velocity is 0 at that point because I haven't let go yet. I let go of it, it has its maximum acceleration at maximum amplitude, maximum position, which is amplitude. And then it speeds up, loses its position, its acceleration goes down until it gets right here. It has no acceleration and no position, but maximum velocity. And then it starts going the other way, compressing the spring. As it compresses the spring, it starts to slow down, but its position's increasing to the left. And so it's going up to amplitude, and its acceleration is increasing. And then it stops and goes the other way, and it keeps doing the same thing back and forth. That's classic simple harmonic motion. Now, I want to look at graphs of this. And the graphs come from something moving in a circle. And I'm going to show you a video clip here in just a second, taken from a cylinder, a little lab mass on that rotating disc platform of mine. And we look at it from the side. And when you look at it from the side, you actually see, instead of seeing it going like that, when you look at it from the side, you'll see the mass go back and forth like that. And it shows you a connection between simple harmonic motion and circular motion. Now the cylinder is on the disc, and the disc is going to go around in a circle. Notice the sine wave form of the x and the y axis for the circle, and notice that for the velocity, and that's the graph right below. And now we're going to compare that to the same motion viewed from the side. Now when you view this from the side, you'll see the disc go right and left as if it's in simple harmonic motion. The equations of simple harmonic motion are related to the equations of circular motion. And I hope you see that there's a sinusoidal pattern for the position time graph at the top and a sinusoidal pattern for the velocity time graph down below. Now the next thing is we'll actually look at the equations of these graphs.